Hi folks, as I promised in the previous episode, today I want to show you a couple things I've been working on for the last couple of months, and didn't really want to go public with it yet, but after Randy Bush at the RIPE meeting in Warsaw came up with Cryptech, which is an open source, open design, open whatever project doing crypto hardware, I at that point decided I better tell people that I'm working on something they might actually use, which is a hardware random number generator, which is supposed to be fit for cryptographic purposes at some point. And today I want to talk about is how the overall design works, what I've done so far, and more specifically on the noise generator, the analog noise generator that I have built and that I'm currently testing things with. Okay, why another random number generator? I mean, you can buy these things already, but in the past I've seen some really ugly stuff going on with various vendors selling stuff that was allegedly crypto, strong crypto, which actually wasn't. If you want to know more about these problems, I've done a talk on this about 2 years ago, so before Ed Snowden and the Heartbleed bug in OpenSSL. And at the Easter hack in Stuttgart over the Easter weekend this year, I've done a rerun on that. It's available on YouTube. Just don't get scared away by me being introduced in German. I do the actual talk in English, and yes, it's actually about an hour and a half, but plenty of stuff in there, plenty of broken things that have been sold as security stuff over the years, and what you can expect from crypto, what you can't expect from crypto, and all that sort of stuff. So my goal is to build a hardware random number generator which is fit for cryptographic purposes, and which has the one property that allegedly is impossible, which is that you, well, at least some of you, as somebody equipped with an oscilloscope and maybe a basic multimeter, can actually check yourselves. And two goals there: make it possible for you to detect if somebody has tampered with your equipment, and more importantly, gives you a chance to figure out if an entire product series or model series have been systematically enhanced, if you like, because apparently even these things happen. And first question is, what do we have to do to achieve these goals? Well, first off, I'm using components that you can check yourself. So no ultra highly integrated ICs, which are ultra secure, allegedly, and you have no option to check what they're doing. Second thing is, use standard components which are not crypto specific or random noise specific or anything, but devices you find in so many different circuits that it's pretty much impossible to sneak something in there. Just economically infeasible is probably the better word for that. Makes it really expensive for certain people. So that's that. And the third thing is, make it diverse. It doesn't make sense if the whole world uses one trusted or trustworthy, allegedly, platform module, whatever you call them, or a handful of different models. The key idea is to make it possible to build variations. Different models, different things, replace things with other stuff that you might like better, and so on. Makes it harder for any potential attackers, which is, in my opinion, good. Okay, That means, of course, that yes, you will get full documentation, which basically starting with including schematics, including source code, including whatever it takes to build and modify these things. I'm not going to release what I have right now because it's work in progress and I'm still doing testing, but before I actually get this to a point where I'd call it a release, yes, I will make these things public. Good. So that's what this is all about. Next question, just a quick one because I'll do that in a later episode in more detail. Why is randomness so difficult? Because you can't really test it. If I give you a device and tell you this is generating random numbers, you can't tell from the outside doing some sort of black box testing if that's true or if it isn't. And the basic proof, slightly simplified, but that's pretty much what these cryptographic pseudo-random number generators generally kind of do, is you take an input stream of zeros, which are not really that random, send them through some state-of-the-art crypto algorithm with a key that you know but you don't tell anybody, and sell the output as random. And if anybody actually manages to prove or show that this output is not as random as you claim, that person has broken whatever crypto algorithm you've used, which is quite a feat, especially if they don't even know what you're using. So that's the key problem when it comes to hardware random number generation. And then there's something else. When we talk about crypto hardware modules, HSM, hardware security modules, that's the general term. These are frequently made tamper resistant, or at least tamper evident, possibly even tamper proof if you believe in marketing words. And that makes sense with devices that actually keep key material inside. You don't want somebody else to extract the key material. However, with a random number generator, a real hardware random number generator, there is no such key material or whatever, so there's nothing to protect. The only thing you get from making these things tamper-proof is you deny yourself the possibility, or deny the end users the possibility to actually take a look at these things are clean or not. On the other hand, a crypto device you can kind of check by just feeding it some input and checking the output, because they are deterministic devices, unlike a random number generator. So that's the situation. Now, next question is, what could we use as random source? You take a look at some slightly older textbooks and it says, yeah, take some radioactive decay, basically grab a barrel of long half-life nuclear waste from your local nuclear power plant, stick a Geiger counter inside and just use that as a random source. Well, folks, don't touch this stuff. It's just unhealthy. Aside from that, if you want to carry this stuff with you and have to fly somewhere, you might find yourself in a situation where people ask you some really awkward questions. No good. So, second source, people use radio noise, radio static. Yes, that might be possible, but it's not my area of expertise, and I don't know how easy or difficult it is to manipulate that using some sort of transmitter. No idea really. Aside from that, radio receivers are a bit more complicated than I want, so that's out of the game as well. Third option, which Caspar mentioned in the forum with the last episode, is thermal noise from a resistor or several resistors. Yes, works, but he used a 8-stage amplifier using op amps for amplification. Way too complicated. Probably a good idea, but no, I can do something simpler than that. What else do we have? CCDs, the camera CCDs, charge coupled devices, which are used as a film sensor or picture sensor in a camera. Yeah, you put them in a dark room, no light coming in, and they generate noise. The very noise that makes your low light pictures look all grainy. You can actually get that with no light at all and can use that as a random noise. Problem there is these CCDs are a bit more expensive and they are difficult to take a look at inside, and that makes things unnecessarily complicated and difficult to audit, which is really the whole idea behind the design I want to do. So what I found left was the Avalanche effect in reverse biased bipolar PN junctions. There are two ways to do this. One is take a standard, usually NPN transistor because they're more popular, reverse bias the base emitter junction and pump up the voltage to the point that there's a breakdown. Problem with transistors is that breakdown might be kind of permanent. The other device you can use, which is meant to take this sort of abuse, is called a Zener diode. However, it's not a Zener diode, it's an Avalanche diode. It's just called a Zener diode, which are diodes, if you reverse bias them, they first behave like a regular diode. They go high impedance, and once you raise the voltage to a point as given in the specification of the given Zener diode, they have a breakdown and current goes through despite the diode being reverse biased. Now, there are two effects there. One is called the Zener effect, which gave them this name, which is that individual electrons go through the junction barrier. Creates noise, yes, pretty low noise, so you need serious amplification to catch that, and that happens at low voltages. If you raise the voltage, eventually electrons go through, but they also kick loose additional charges, electrons, within the reverse bias junction, and that leads to an avalanche effect. So it's called avalanche effect, and these diodes should be called avalanche diodes, but because everybody calls them Zener diodes, well, we stick with the name. And that actually works. There's a burst of current going through a Zener diode when there's this breakdown. Eventually the junction area is more or less depleted of mobile charges, and they recover. Gives you very nice noise. Actually has some pretty nice properties which make good random number generation. Basically means there's no arbitrary long times between those bursts, and that's good because you don't want to wait forever for the next few bits, but it is highly unpredictable, which is cool. And the best thing about it is these things are tremendously simple to build. The current noise generator core, the noise generator proper I use, takes a Zener diode, or Avalanche diode, obviously, takes two capacitors, same value actually, doesn't really matter what you use there, or makes very little difference, two unfortunately different type transistors, more about that in a moment, and 5 resistors. And then there's power LED plus series resistor just for testing on the board I use, and then there's test pins, so you can actually take a look inside with an oscilloscope, see what's going on there. That's what I'm doing, and that's the first stage to do. From there it goes into a microcontroller, which turns the analog noise into something that's basically a random bit stream, and then can feed it to a computer, which might use it as is, or might use it to seed a pseudo-random number generator, or do some post-processing to get some really high quality, whatever that means, random bit stream. Okay, and I guess right now it's time to grab the camera, put it on the bench, because, well, there's some stuff to show you, and take a look at things in more detail. Okay, so here's what I'm currently working with. Here's the actual generator module I'm using right now. It has the generator proper on here and the step-up converter, because I need, for the Avalanche effect to work, at least about 9 volts. I'm using a generator here which generates 13.5 volts. Originally tried with 12 volts, but when I built this, I actually realized if I go for 13.5 volts, I can use some basically E3 series resistors rather than going for E12. So it might be easier to build this from whatever stuff you have lying around. This is what I want to talk about today. From there, it goes on to a microcontroller. This is just some homemade test evaluation whatever board. This is an Atmel ATtiny 2313, which is probably the best choice for this sort of stuff, unless I have a way to connect this right away to a computer like a Raspberry Pi, which has an SPI interface, so I can avoid going through a serial interface, which then goes into an FT230 through RL serial to USB adapter, which then connects to pretty much any computer. Right now I'm using the FTDI chip, because I want to make this work with as many computers as possible, but, well, there are ideas I have which might actually lead to a point that I can remove that in some situations. So this is the stuff I'm working. By the way, this is an ISP programmer, so I can use the Raspberry Pi to program the microcontroller. First question probably is, why on earth do I use a Raspberry Pi? 2 reasons for that. First off, if anything goes seriously wrong, I'd rather fry a 40 euro Raspberry Pi than an 800 euro notebook. And second one is, if the Raspberry Pi can handle this, then so can a cell phone, a smartphone, or a tablet, and with a real proper PC class computer, the system load should be quite reasonable. So, and this is, by the way, this is just a USB hub. You can actually get them built like this. Yeah, and that's all this going on right now. What I'm currently doing, and I'll have more to tell about that in the next episode, I'm currently generating test data, collect them on here, and do some statistic tests to see if the generator is any good, which takes literally weeks, which makes this so excitingly meditative. Okay, so much about what I'm working with right now. And to give you an idea how I got to this point and how this works and why it works like this, I guess we should just move this beautiful little plywood thing out of the way. Hang on. And I love these for this very job. Grab another one, so I know where the camera picture starts and ends without having to look at the camera display. And a bit of the history, how I did this, the problems I ran into, the decisions I made and why I made them. First off, the Zener noise is fairly low. And what's rather annoying and makes it this something where you actually have to experiment is that the datasheets don't tell you how much noise they generate, at least. It's always, because normally you don't want the noise. Noise is no more than blah blah. So that involves some experimenting, but, well, that's part of the fun really, isn't it? So first thing we need is something to amplify the signal. What did I try? LM232 quad op amps. Kind of works, but is tremendously slow. Why? Because their bandwidth gain product is abysmal. So at that point, one option would have been to go for high frequency op amps. But if I want to stick with general purpose, widely used components, well, these are out. What's next? Okay, standard transistors. These are the ones I generally have lying around somewhere. It's BC337 and BC547C. And found out that the BC547C has a higher frequency range. So, yeah, I stuck with that. Works, at least for starters. So, I built my first board. Looked like this. So, very simple. 2 transistors, a Zener diode, couple resistors, connectors, couple capacitors. It's a big label, so I know where to connect what. This is strip board, and you can see my breathtaking soldering skills, but don't knock it, it works. And I normally solder things late at night when I'm too tired to sleep, really. While other people watch TV all night and still can't fall asleep for some reason. It worked. Good. Well, kind of. The connectors, and this is something I've stuck with throughout this entire project. On the right hand side I have ground, 5 volts, and the output, which is basically kind of TTL level analog noise. And left hand side, ground, 5 volts, and this is the 12 volt input. So I can connect some 12 volt source there. Well, for first try, not too bad. So next thing I did was built the same thing using perf board. And what I did here is, I normally do this when I build circuits like this, use circuit design tool. In this case I've used KiCad, design the board, and you see I've used BlueTack, which is white here in Germany, to stick it to one of these plywood boards and solder it up using well, copper wire and the leads on the through-hole components and whatnot. And it worked. Great. Output wasn't overly fast, but was a starter. Then I realized I made a mistake, which is, well, no test points. So next design, I added a couple test points to hook up my oscilloscope to. Yeah, that was getting the right way. So time to bring out the breadboard again and optimize for performance. First thing I've done was decrease the amplification on the transistors and use 3 of them in a row. And yeah, result was okay. But 3 transistors, wow. And speed was not that exciting either. So I decided, give it another try. Got myself some, what are those, BF959 high frequency transistors, significantly faster for the job. They get much faster out of saturation than the BC547Cs, but their gain is way less than the BC547. So, next board. At this point I switched to Eagle. And yes, I just got myself a license. There's a free version of that, which is good enough for this job, but you're not supposed to use for commercial projects. And if I ever turn on monetization on YouTube, I don't want any discussion. So I spend a whopping 70-something euros on an Eagle license, which is fair money, and it runs on Linux, so I don't have to use Windows for this. However, when I first tried, the result was, well, I didn't really get along too well with Eagle first, so this board got really big. By the way, the backside looks something like this. Takes a lot of time, but it works. 3 of those BF959s. The device worked, but I thought, well, maybe if I'm smart, I can get rid of one of the transistors again. And eventually that led to what I'm currently using. This is the design I'm currently using, and it's just the core circuit of what I've got running for the test right now. 2 transistors. The first one is a BC547C because it has a higher gain, and at this point it doesn't go into saturation anyway. And then that followed up with a BF959, which might actually go into saturation sometimes, but gets out of it again much faster. So, did the test pins. I eventually decided make an extra ground pin that I can easily hook up to the oscilloscope, and you have altogether 6 test pins for the board. Well, yeah, and that's what I'm using. Actually, I might show you what this generates as output at some time, so we'll just leave it here. Next question was, how do I get 12 volts? Well, easiest thing to do is use an external 12 volt power supply, then just use a standard 7805 to get 5 volts from out of that. And yeah, worked, but this is just for breadboard stuff. So didn't use that. Once I got this work, I built, well, again, strip board and again, Bluetech on there to provide me with 12 volts and 5 volts from an external power supply. Worked, but is a bit impractical. Since my goal was to power this from a USB port or from some sort of 5 volt or whatever source from an SPI capable Raspberry Pi or BeagleBone Black or something like that. Well, yeah, I'll keep this, but won't be of much use for now, so might as well use it some other way. So next thing I did was, first I needed a 5 volt power supply like USB. And well, easiest way to do, take a USB cable, take a USB cable, add a 100mm connector to it, and use some ultra high-tech power supply. Yeah, the reason why I didn't even bother to get myself a linear power supply, which I don't even have because I've never really needed one, was I wanted to make sure that this works if there's a switching power supply involved. So it doesn't make sense to test everything with a linear power supply and everything works fine, and then you hook it up to a noisier switching supply and things break again. So I'm using that. Keep that together. And what would I use for a step-up converter? I've got these from Pololu. These are very, very nice little devices. Hang on. Paid about 13 euros for these. These step-up converters go from 4 to 25 volts. There's a little trimmer pot here. Very nice for testing what happens if you change the voltage on the circuit. And yes, I'm going to show you the circuit as well in a moment. Once I realized, okay, if you go higher than 12 volts, the power consumption goes up by the square of the output speed and the voltage. I decided, okay, 12 volts is fine, and got rid of that and got myself, or used one of these, which are about 4 euros, another Pololu chip. The only thing I really wonder, they're cool. I mean, for the money you get, you can't build these for that money yourself. The only thing I really wonder is what the step-up converter on here is. I think I may have found it on, I don't know, DigitKey or Mauser or Farnell or something, but I'm not entirely sure. And of course, using this for the project is not really an option, simply because with all the SMD stuff in there, you can't even get a multimeter probe or oscilloscope probe in there. And the goal is to make things testable. So nice, but well, for testing, yes, but not for the final thing. At that point, it was breadboard time again. And oops, sorry. This is a run-of-the-mill MC34063 step-up converter, set up like according to the datasheet, except that I've been rather generous on the inductances and the electrolytic caps to minimize ripple, and yep, worked right from the start. So basically we keep that as well. Together they are the equivalent of the thing I'm currently using for testing, but I don't want to stop the tests, so well, this is what I want to show you today. And next episode I'm going to talk about the microcontrollers and interface chips and whatnot. But right now let's just hook this stuff up and connect to a scope. This is what you get when you turn it on, and that looks kind of, well, messy, which is good because we want it to be messy, or rather noisy. And when we move the signal down, this is, and the trigger up, this is kind of the output you get, which looks, well, noisy, cool. And yes, we can take a couple single snapshots. We can take a look at the broader distribution. Great. And we can also take very close look, whatever. Anyway, this is noisy and fairly evenly distributed. No long stretches of nothing going on or anything like that. So that's pretty cool. And before we hook up the next the second probe, I guess it's time to explain the circuit. So this is the circuit I use, and as you see, it's not overly complicated. Nevertheless, it takes a bit of explanation. Here we have the Zener diode, and we have the first stage transistor. And let's assume for now that we power this thing on. What happens? The capacitor here is discharged, so we hook up 12 volts or whatever here, and first thing that happens, the transistor goes high impedance, so we have a current charging up the capacitor. At some point we reach the breakdown voltage of the Zener diode, and then things start to work. Eventually the Zener diode breaks down, creates, or Avalanche diode creates a burst of current going through the transistor, which means we have a significant current going from collector to emitter, which means we get a series voltage drop here. Yeah, and that's the signal. Eventually the avalanche stops, and at this point the transistor goes high impedance again, and the voltage here goes up because it's connected to 12 volts through the 1K resistor. Figuring out the values, the capacitors here and here are not overly critical. The resistors control to some degree the amplitude and this frequency spectrum, and yes, I've just experimented with those, largely because they depend on properties of the Zener diode which you don't even find in the datasheet. Well, at least I didn't. So here we have our first stage noise. We'll look that up in a moment. Run that through a resistor and capacitor for AC coupling into a second stage amplifier. This was the easiest thing I could come up with. The 56K resistor here biases the base of the second transistor, so it's roughly at 2.5 volts if there is no signal coming in. And the resistors here and here pretty much determine the amplification on here with this transistor. And what we get here as output is what we've seen in the oscilloscope, which goes from something about from 0.5 to 4.5 volts or so, which is perfectly fine to feed at least into an Atmel microcontroller. So at this point we've measured here the actual output. What we can also do is measure here and take another look at what comes out at this stage. And now when we take a look at the oscilloscope, we see the blue line is the first stage output, the yellow one is what we actually get from the entire circuit. A couple things we can do: set the bandwidth limit to 20 megahertz on each. And what's then useful is to invert the first stage signal. And you see here that the yellow signal is kind of delayed and smoothed out, and well, generally follows the first stage signal, which is pretty much all we need right now. So at this point we have a working noise generator. That's the noise generator I've built, and how it works and why it works the way I've built it and what my goals were. And I hope you found this interesting. Next episode will be about how to connect that to a microcontroller, how to turn analog noise into series random numbers, and from there how to get stuff into the computer, because there are a couple more things going on there. But for today, let's call it a day. I hope you enjoyed it. If you have any ideas about this, if you want to help me out with the statistics stuff, because that's not really what I'm good at. I've done well, combinatorics, discrete probabilities for randomized algorithms, but doing statistical analysis has never been anything I've been working on. If you want help, leave a note in the forum. If you have better ideas, complaints, whatever, let me know, because this is really something I could need some help. If you're an electrical engineer and have sort of, oh, how could you possibly build that? I'm sure I could use some help there. What I've learned about electronics was not from 2 semesters of electrical engineering for computer science undergraduates, because that was complete crap. That was all just stuff I've learned 30 years ago when I was a high school student and tried to mess around with this sort of stuff in the afternoon. Anyway, if you have questions, whatever, leave a note in the forum. If you watch this on YouTube, liked it, do me a favor, give it a thumbs up. I'm just about to turn on monetization, so, well, basically to improve visibility. And if you know anybody who might be interested in this, point them towards this. I mean, okay, I'd like to do this generally for the forum, but this thing is eventually bound to be a community thing, because I can't introduce diversity here. That's what you have to do. I can show you how I've done it, and then you decide, yeah, but I might do it different, and that'll give certain people a hell of a time, which is the point about this, really. Okay, so much about this, and hope you enjoyed it, and hopefully see you again, well, hopefully next time with the microcontroller hookup. Bye.